Welcome to Entri App. Today we are starting with our basic subject in chemical engineering, that is process calculation. So in process calculation mainly the questions are based on material balance. Okay. So from introduction we have some units and dimensions. Basically we already discussed about units and dimensions in +1 subject and +2 subject. Okay. So here you only concentrate on the primary quantities such as length, mass, time and temperature. Suppose length L and mass M, time T and temperature theta. These are the commonly used basic measurements. Okay. So nowadays there will be no questions from this area, but basically we have to discuss mainly this thing I discuss about due to sometimes we have to know about some conversions based on this length, mass and time. Suppose 1 hour is 3600 second, 1 hour is 60 minute, and in the case of length the conversion from feet to meter, it's 1 feet is 12 inch and that is equal to 0.3048 meter. Okay. Then mass there is a conversion from pound to kilogram. Sometimes we need that conversions in some material balance problems. Okay. But in basically the primary quantities problems are not included in nowadays in the GATE problems. Then we start with the mole concept. In material balance with chemical reaction we have to some basic knowledge, we have to concentrate, we have to make some basic knowledge for calculating number of moles and how the stoichiometry calculation is depends on this number of moles. So initially what is mole? The definition of mole is the amount of substance that contains as many particles or entities as there are atoms in 12 gram of carbon 12 isotope. So 1 mole definition is based on 12 gram of carbon 12 isotope. If we take 12 gram of carbon 12 isotope, it contains Avogadro number atoms. So for getting this Avogadro number, how much amount of substance is taken, that is defined as 1 mole. Then 1 mole of sodium atom, that means it contains Avogadro number sodium atom, and 1 mole carbon atom contains Avogadro number carbon atoms. 1 mole carbon dioxide molecules contain Avogadro number carbon dioxide molecules, and 1 mole of ammonia gas contains Avogadro number ammonia molecules. So the amount contains the amount of 6.023 in 10 raised to 23 ammonia molecule is defined as 1 mole of ammonia. Okay. 1 mole of carbon dioxide, that means it contains Avogadro number carbon dioxide molecules. Okay. This 6.023 in 10 raised to 23 is Avogadro number. Okay. Then molar mass. The mass of 1 mole of a substance in gram is called its molar mass. So we are familiar with the molar mass of carbon, hydrogen and oxygen. Molar mass of carbon is 12 gram and oxygen is 16 gram, that is oxygen atom is 16 gram and oxygen molecule is 32 gram. So GMM, that is molar mass of oxygen atom, we can write it as GMM of oxygen molecule, GAM of nitrogen atom, GMM of nitrogen molecule, GAM, that means gram atomic mass of oxygen atom, GMM, gram molecular mass of oxygen molecule. So these are the basic, but we have to study the basically the atomic mass of some element. For hydrogen 1 gram and for oxygen 16 gram and for nitrogen 14 gram, carbon 12 gram, then sodium 23 gram, calcium 40 gram, magnesium 24 gram, sulfur 32 gram, phosphorus 31 gram, chlorine approximately 35.5 gram and potassium 39 gram, iron 56 gram, copper 63.5 gram and silver 108 gram. These are the common elements. Okay. Sometimes in stoichiometric problems, if the methane combustion, the process is methane combustion. So, we have to calculate the molecular mass of methane. In methane combustion, the reaction between methane and oxygen. So, the products are carbon dioxide and H2O. Okay. So, in stoichiometric calculation, we need to calculate the molecular mass of methane, oxygen, carbon dioxide and water. So, we have to study about this molecular mass or atomic mass of these elements. These are the common elements. Okay. You have to study the atomic mass of these elements. Then, how can we calculate the number of mass? If the given mass of a substance is given, the mass of a substance is given in gram, then we can calculate number of moles by given mass divided by GMM or GAM. Given mass divided by gram molecular mass or gram atomic mass. This is the basic equation for calculating number of moles. So, we can write it as N is equal to W divided by M, where W is given mass in gram, M is molar mass. So, the unit of molar mass is, if it is gram, this is in gram per molar, we can write it as the unit of number of moles is mole. Okay. Then, if the given mass in kilogram, then we can write molecular mass in kilogram per kilomole. Okay, kilogram per kilomole. Then the unit of number of moles is kilomole. Okay, kilogram by kilogram per mole. Then the unit of number of moles is kilomole. Gram per mole. Then the unit of number of moles is number of moles, or we can write it as gram mole. Okay, gram mole or mole. This is kilomole. If we take given mass in kilogram, then number of moles in kilomole. Then stoichiometry and stoichiometric calculation. The quantitative study of reactants required or the products formed is called stoichiometry. Using stoichiometric calculation, the amount of one or more reactants required to produce particular amount of product can be determined. For example, in the case of ammonia production, the reactants are nitrogen and hydrogen. Okay. In the formation of ammonia, the reactants are nitrogen and hydrogen. Nitrogen combined with the hydrogen to form ammonia, and by balancing N2 plus 3H2 gives 2NH3. This is the balanced stoichiometric equation of ammonia formation. Then here nitrogen means 28 gram nitrogen combined with a 6 gram hydrogen, 3 mole hydrogen gives 2 mole ammonia, that is 34 gram ammonia. This is the basic stoichiometric calculation. So, by stoichiometry, if we need 68 gram ammonia, okay, how much amount of nitrogen is required or how much amount of hydrogen is required? So, this basic calculation are based on stoichiometry. Okay. So, if we have 72 gram nitrogen, then how much amount of ammonia can be produced from this amount of nitrogen? That is a basic question. Okay. Or for producing 80 gram ammonia, how much amount of nitrogen and how much amount of hydrogen is required? These are the basic stoichiometric calculations. For example, calculate the amount of water produced by combustion of 40 gram of methane. Okay. So, here the process is combustion of methane, that means reaction of methane with oxygen, reaction of methane and oxygen. The product are, this is a hydrocarbon, means this contains carbon and hydrogen. The product CO2 plus H2O. Then by stoichiometric balance, 2H2O, CH4 plus 2O2 gives 2H2O. Okay, for oxygen. Then here by stoichiometry, 1 mole methane combined with 2 mole oxygen give 1 mole carbon dioxide plus 2 mole H2. And in terms of mass in gram, methane 16 gram plus O2 32 gram, 2 mole O2, that means 64 gram. Then carbon dioxide 44 gram, then water 2 H2O, H2O 18 gram, 2 H2O 36 gram. So 16 gram methane by stoichiometry, 16 gram methane combined with 64 gram oxygen give 44 gram carbon dioxide and 36 gram H2O. The question is the amount of water produced by combustion of 40 gram of methane, that is the amount of methane is given as 40 gram. Then what is the question? The amount of water produced. So based on methane, we have to calculate the amount of product, that is amount of water. So basically by stoichiometry, 16 gram methane gives 36 gram H2O, then 40 gram methane gives how much amount? So just cross multiply 40 into 36 divided by 16, or you can write it as 40 by 16 into 36. Okay, this the basic simplest method is just cross multiply 40 into 36, that is 16, 36, 40, the required amount write it as x. So 16 into x equal to 40 into 36, they are proportional because 1 is to 2, 2 is to 4, these are proportional. So 2 into 2, that is equal to 1 into 4. So 16 gram, 36 gram. Then for 40 gram, x is the amount of water. So 40 into 36 equal to 16 into x. So x is equal to 40 into 36 divided by 16. So amount of water is 40 into 36 divided by 16. So 4, 10, then 9 into 10, 90. Okay, 90 gram of water produced. Okay. Then one more question, calculate the amount of carbon dioxide produced by combustion of 56 gram of methane. So the process is combustion of methane. So the reaction is CH4 plus 2O2 gives CO2 plus 2H2O. So here I concentrate on question, calculate amount of carbon dioxide, the required data amount of carbon dioxide based on 56 gram methane. So by stoichiometry, 16 gram methane give 44 gram carbon dioxide. Okay, we don't need to waste the time for calculating the amount of oxygen and amount of water, because the question is amount of carbon dioxide based on amount of methane. Okay, so 16 gram methane gives 44 gram carbon dioxide, then 56 gram methane gives how much amount of carbon dioxide? So just cross multiply 56 into 44 divided by 16. So 4, 11, then 14 into 11, 154 gram. Okay, 56 gram gives 44 gram, 16 gram methane gives 44 gram carbon dioxide, then 56 gram methane gives 154 gram carbon dioxide. This is a basic calculation. Then one simple question, how many grams of oxygen are in 65 gram C2H2O2? This is a previous GATE question, I think in 1998, 1997, that range. So C2H2O2. Here 2 carbon, 2 hydrogen, 2 oxygen. So 24 plus 2 plus 32. The amount of or molecular mass of C2H2O2 is 58 gram. In 58 gram C2H2O2, the amount of oxygen is 32 gram. Okay. C2H2O2 contains 2 oxygen atoms. So, C2H2O2, the molecular mass is 58 gram. 58 gram C2H2O2 contains 32 gram oxygen. Question is, how many grams of oxygen are in 65 gram of C2H2O2? In 65 gram C2H2O2, how much amount of oxygen? So, just cross multiply 65 into 32 divided by 58. Okay. When we multiply with 65 by 58 into 32, the answer is more than 32. Here there is only one option with more than 32. So, answer is option D, 35.9. Okay. 65 by 58 is more than 1 point something. So, 32 into 1 point something is more than 32, that is 35.9. Then the mass of oxygen required to react completely with 1.5 gram of hydrogen to form water. Here oxygen react with hydrogen. So, the reactants are hydrogen and oxygen, or oxygen and hydrogen. Then product form water, okay, H2O. So, the reactants hydrogen and oxygen, the product is water. Then mass of oxygen required to react completely with 1.5 gram of hydrogen. So, based on hydrogen, how much amount of oxygen is required to form water? So, by balancing 2H2 plus O2 gives 2H2O. So, stoichiometrically 4 gram hydrogen combined with 32 gram oxygen give 36 gram water. So, here 4 gram hydrogen gives 32 gram oxygen. So, 1.5 gram hydrogen gives how much amount of oxygen? So, 1.5 into 32 divided by 4. So, 8 into 1.5. 8 into 1 plus 4, 12 gram. 8 into 1.5, 12 gram. Okay. Then same type, the mass of hydrogen required to react completely with 48 gram of oxygen to form water. So, here also the reactants are hydrogen and oxygen. 2H2 plus O2 gives 2H2O. This is the balanced chemical equation. Then 48 gram oxygen. The mass of hydrogen required. So, basically 4 gram hydrogen combined with 32 gram oxygen. So, for 48 gram oxygen, the mass of hydrogen required is the question. So, 48 into 4 divided by 32. So, 6 gram. Option D, 6 gram. These are the basic calculations in stoichiometric based. But in nowadays in GATE chemical engineering, questions from this area, I already told that mainly based on material balance. So, we need to make a strong concept in this stoichiometric calculation. After that, we can do the material balance problem very easily. Okay. Then next are limiting reactant and excess reactant. These are the common term in our process calculation. What is limiting reactant and what is excess reactant? The limiting reactant is the reactant which is completely consumed or completely reacted. Okay. And this limiting reactant, excess reactants are possible if there is more than one reactant. Suppose 2H2 plus O2 gives 2H2O, N2 plus H2 gives NH3, that is N2 plus 3H2 gives 2NH3. Then suppose CaCO3 gives CaO plus CO2. Here there is only one reactant, that is calcium carbonate. In this case, there is no limiting reactant, there is no excess reactant. Okay, because the amount of product is only depend on the amount of calcium carbonate. But in these two cases, the amount of product water is based on the amount of hydrogen and oxygen. here the amount of ammonia is based on the amount of nitrogen and hydrogen. So, there is a chance of limiting reactant and excess reactant. Okay. In stoichiometrically, 4 gram hydrogen need a 32 gram oxygen. Okay. Here 28 gram nitrogen need a 6 gram hydrogen. So, in the reactor, the amount of nitrogen and hydrogen, if we give it as 28 gram nitrogen and 6 gram hydrogen, we get a 34 gram ammonia. Okay. So, instead of that, I give 35 gram nitrogen and 6 gram hydrogen. So, 28 gram nitrogen combined with 6 gram hydrogen gives 34 gram ammonia. Then extra 7 gram nitrogen other. So, this 7 gram nitrogen is in this product stream, because there is no more hydrogen for reacting with this 7 gram nitrogen. Okay. So, nitrogen is the limiting reactant. Sorry, nitrogen is the excess reactant, because there is a extra amount of nitrogen, that is 7 gram nitrogen is in product stream, that is nitrogen is excess reactant, and here hydrogen is limiting reactant. Okay. So, what is limiting reactant? The reactant which completely consumed. Okay. Hydrogen is completely reacted and converted into ammonia. Here 28 gram nitrogen is converted and extra 7 gram nitrogen is in product stream. That means nitrogen is excess reactant. So, limiting reactant is the reactant which completely consumed or completely reacted. The reactant which is completely consumed in a chemical reaction is called a limiting reactant or limiting reagent. And one point is that the amount of product formed is limited by this reagent, since reaction cannot continue without it. Okay. When the 6 gram hydrogen is completely reacted with the nitrogen, the production of ammonia is stopped. Okay. So, the amount of product is always based on limiting reactant or limiting reagent. The amount of product is always based on limiting reactant or limiting reagent. So, next one is excess reactant, the reactant which is not completely consumed in a chemical reaction. The reactant which is not completely consumed in a chemical reaction, that is called excess reactant. It is present in larger amount than that calculated by balanced chemical equation. Okay. Suppose N2 plus 3H2 gives 2NH3. 1 mole nitrogen combined with 3 mole hydrogen gives 2 mole ammonia. So, into the reactor I give 6 mole nitrogen and 12 mole hydrogen. Okay. So, by stoichiometry 3 mole hydrogen need 1 mole nitrogen. So, for 12 mole hydrogen we need 3 by 1. For 4 mole nitrogen plus 12 mole hydrogen. This is the stoichiometric ratio. For 1 mole nitrogen, 3 mole hydrogen is required. So, for 4 mole nitrogen, 12 mole hydrogen is required. Here 12 mole hydrogen and 6 mole nitrogen is fed to the reactor. Okay. That means 2 mole, 6 minus 4, 2 mole nitrogen is in excess. So, that means nitrogen is the excess reactant, nitrogen is the excess reactant and hydrogen is the limiting reactant. So, 1 mole nitrogen combined with 3 mole hydrogen gives 2 mole ammonia. So, 4 mole nitrogen combined with 12 mole hydrogen gives 1:4 8 mole ammonia. So, if we give 6 mole nitrogen plus 12 mole hydrogen gives 8 mole ammonia plus excess amount, that means 2 mole nitrogen. Okay. All of the material balanced questions are based on percentage excess of air or percentage excess of oxygen. Okay. So, the limiting reactant, the excess amount, these are the basic calculation in material balance including chemical reactions. Okay. The next one question, 3 moles of dinitrogen and 12 moles of dihydrogen are mixed to produce ammonia. Calculate the amount of ammonia. In this question, 3 moles of dinitrogen and 12 moles of dihydrogen. 3 moles of dinitrogen and 12 moles of dihydrogen. That means the amount of two reactants. Here the reaction is N2 plus 3H2 gives 2NH3. 3 moles of nitrogen and 12 moles of hydrogen. So, given data includes the amount of nitrogen and the amount of hydrogen. If the questions are based on limiting reactant or excess reactant, the two reactants amount must be given in the question. Okay. Otherwise, the amount of ammonia formed based on 3 moles of nitrogen, the amount of ammonia formed based on 12 moles of hydrogen. These are the basic stoichiometry calculation that does not need to identify the limiting reactant or excess reactant. But here 3 moles of nitrogen and 12 moles of hydrogen are given. Okay, 3 moles of nitrogen and 12 moles of hydrogen are given. So, first you have to identify which one is the limiting reactant. So, easily we can identify that the given values are 3 and 12, 3 mole nitrogen and 12 mole hydrogen. In stoichiometric data, 1 mole nitrogen combined with 3 mole hydrogen, that is 1 3. Okay, 1 mole nitrogen, 3 mole hydrogen. These are the stoichiometric ratio. 1 mole nitrogen combined with 3 mole hydrogen, and the given data is 3 mole nitrogen and 12 mole hydrogen. So, just 3 by 1, 12 by 3. That is, in the case of nitrogen, given data 3 mole, stoichiometric data 1 mole. In the case of hydrogen, given data 12 mole, stoichiometric data 3 mole. So, 3 by 1, 12 by 3. Here 3 by 1 is equal to 3, 12 by 3 is equal to 4. Comparing 3 and 4, 4 is greater than 3. So, we can identify that simply this is the limiting reagent and this is the excess reactant or excess reagent. Okay. This is the limiting reagent and this is the excess reagent. Okay. So, based on limiting reagent, the amount of product formed. Based on limiting reagent, the amount of product formed. So, 1 mole of nitrogen gives 2 mole of ammonia. So, 3 mole of nitrogen gives 6 mole of ammonia. That means 6 into 17 gram. 6 into 17 gram. Okay. That means 102 gram. So, here in the based on limiting and excess reactant questions, you have to notify that this 3 moles of nitrogen and 12 moles of hydrogen. That means the amount of both reactants are given in the question. So, first you have to identify the limiting reactant. Limiting reactant. So, simple method is first write the given data, then divide with the stoichiometric data 3 by 1, 12 by 3. So, which one is the less value? That is the limiting reactant, other one is excess reactant. Then one more question, 56 gram nitrogen and 16 gram hydrogen are mixed to produce ammonia. Calculate the amount of ammonia formed. Here the amount of nitrogen and amount of hydrogen, these are the reactants. So, in this question the amount of both the reactants are given. Okay. So, by stoichiometry, N2 plus 3H2 gives 2NH3. First identify the limiting reactant. The given data are 56 gram and 16 gram. So, here the amount is in gram. So, we can take the stoichiometry in gram. 28 gram combined with 6 gram gives 34 gram. So, divide nitrogen 56 by 28, 16 by 6. 56 by 28 is 2, and 16 by 6 is more than 2, something 2.6. So, which one is limiting reactant? Nitrogen is the limiting reactant. 2.6 is greater than 2. So, nitrogen is the limiting reactant and hydrogen is the excess reactant. So, the amount of product is always based on the limiting reactant. So, 34 gram ammonia required 28 gram nitrogen. So, here the amount of nitrogen is 56 gram. Then the amount of ammonia produced is based on limiting reactant. Here nitrogen is the limiting reactant. So, 28 gram nitrogen gives 34 gram ammonia and 56 gram nitrogen gives 68 gram. This is the double value. So, 68 gram. Okay. Then one more question, 6 moles hydrogen react with 2 moles of oxygen. The limiting reagent is 6 moles of hydrogen react with 2 moles of oxygen. The limiting reagent is. So, basic equation is 2H2 plus O2 gives 2H2O. Hydrogen and oxygen are the reactants. Given data are 6 moles and 2 moles. Here 2 and 1. So, 6 by 2, 2 by 1. 6 by 2 is 3. So, hydrogen is the excess reactant and oxygen is the limiting reactant. Okay. Which one is 2? 3 is greater than 2. So, oxygen is the limiting reactant. Okay. So, the amount of product is always based on limiting reactant. Here the question is limiting reagent. So, oxygen is the limiting reagent, option B. Then in solutions mainly the terms are solute, solvent, molarity, molality, normality. We are familiar with these terms molarity, molality, normality, and mole fraction, weight fraction, volume fraction, or mass fraction, or mole percentage, mass percentage, volume percentage. So, in solutions are homogeneous mixture containing 2 or more components. The component which is present in larger quantity is called solvent and lesser quantity is called solute. Then sodium chloride solution, sodium chloride is the solute and water is the solvent. Okay, substance which is dissolved is called solute and the substance in which solute is dissolved is called solvent. Suppose in sugar solution, sugar is the solute and water is the solvent. And a solution containing only 2 components, they are called binary solution, and if the solvent is water, it is called aqueous solution. So, the aqueous solution of methanol, that means the components are methanol and water. Okay. Aqueous solution of ethanol, that means ethanol and water. So, 2 components we can termed as binary solution. Okay. Binary solution. Then first one, mass percentage. It is defined as number of parts of solute present in 100 parts by mass of solution. Simply consider a binary mixture of A and B. The mass of A, let us take the mass of A is WA and mass of B is WB. Okay. Then mass percentage of A, that is equal to individual mass divided by total mass into 100. This is mass percentage. Okay. Suppose if there are 3 components, then the mass of A is WA, mass of B WB, mass of C is WC, then mass percentage of A is WA divided by WA plus WB plus WC into 100. That means individual mass divided by total mass into 100. So, weight fraction or mass fraction. Similarly, let us consider a binary mixture of A and B. Then mass of A is WA, mass of B is WB. Then WA divided by WA plus WB. This is mass fraction of A or weight fraction of A. Mass fraction of A or weight fraction of A. WA divided by WA plus WB. Then what is the difference between weight percentage and weight fraction, or mass percentage and mass fraction? If we multiply this fraction with 100, then it will be weight percentage. Okay, if there is no 100, only ratio WA by WA plus WB, that is individual mass divided by total mass, that is fraction. Okay, when we multiply with 100, it will convert into percentage. Okay, then next mole fraction. Similarly, the number of moles of A, consider a binary mixture of A and B. Then let us take number of moles of A is Na and number of moles of B is Nb. Then mole fraction, I write it as mole fraction of A is Xa. Okay, then Xa is equal to individual number of moles divided by total number of moles, Na divided by Na plus Nb. Okay, the ratio of number of moles of a particular component to total number of moles. Okay, individual number of moles divided by total number of moles, Na divided by Na plus Nb, that is mole fraction of A. Then mole fraction of B is equal to Nb divided by Na plus Nb. Okay, mole fraction of B is equal to Nb divided by Na plus Nb. Okay. The next volume fraction. Similarly, volume of a particular component divided by total volume of all the components, Va divided by Va plus Vb, or Va divided by Va plus Vb plus Vc. So individual volume divided by total volume. Then when we multiply this fraction with 100, it will be converted into volume percentage. So mole fraction into 100, that is mole percentage. Weight fraction into 100, that is weight percentage. Then next the solution related concentration terms are molarity, normality, molality. First one is molarity. It is number of moles of solute present in 1 liter of solution. Number of moles of solute divided by volume of solution in liter. Volume of solution in liter. The next normality. Here the numerator is number of equivalents of solute divided by volume of solution in liter. The denominator is same as molarity, but numerator is number of equivalents of solute. In the case of molarity, number of moles of solute. Here number of equivalents of solute. We have number of moles can be calculated by given mass by molecular mass. But in the case of number of equivalents, given mass divided by equivalent mass. Equivalent mass is, suppose in the case of sulfuric acid, the molecular mass is 98 and equivalent mass is 98 divided by 2, that is 49. So equivalent mass calculated by dividing the molecular mass with the valency. Okay, here in the case of H2SO4, the valency is 2. Either you can calculate total positive charge or total negative charge in the case of acid, salt, base. Okay, here the total positive charge is 2H plus. So molecular mass 98 divided by 2, 49. In the case of HCl, hydrochloric acid, the molecular mass is 36.5 and equivalent mass is also 36.5, because total positive charge is plus 1 or total negative charge minus 1. So 36.5 divided by 1. So in the case of phosphoric acid H3PO4, the valency is 3, and in the case of calcium sulfate, the valency is 2. So equivalent mass is molecular mass divided by valency, and number of equivalents is given mass divided by equivalent mass. Number of moles is equal to given mass divided by molecular mass. Number of equivalents equal to given mass divided by equivalent mass. So normality is number of equivalents of solute divided by volume of solution, or we can write it as normality is equal to molarity into valency. Okay, normality is equal to molarity into valency. The next molality. In the case of molality, the numerator is same as that of molarity. Molarity is defined as number of moles of solute divided by volume of solution in liter. But here molality, which is defined as number of moles of solute divided by mass of solvent in kilogram. Mass of solvent in kilogram. Okay, denominator changed, mass of solvent in kilogram. In the case of molarity, volume of solution in liter. Okay, mass of solute divided by volume of solution liter. In the case of molarity, number of moles of solute divided by mass of solvent in kilogram. Then parts per million, when the solute is present in very small quantity, concentration is expressed in ppm, parts per million. That is defined as amount of solute in gram present in 10 raised to 6 gram of the solution, 10 raised to 6 gram of the solution. Then saturated solution. In saturated solution, we can define the term solubility, that is maximum amount of solute dissolved in given amount of solvent. So, it is a solution, in saturated solution means in which no more solute can be dissolved at the same temperature and pressure. When temperature increases, solubility increases. So, it is defined as the solution in which no more solute can be dissolved. Okay. So, solubility is defined in the case of saturated solution. Solubility means the maximum amount that can be dissolved in specified amount of solvent at a specified temperature. Suppose 2 kilogram sodium chloride is dissolved in 100 kilogram water. So, 2 by 100, okay, solubility 2 by 100, the amount of solute in the amount of solvent. And one more thing is standard temperature and pressure, STP. Okay. The temperature is 0 degrees Celsius or 273 Kelvin, and pressure of 1 atm or 101325 Pascal. Then when the number of moles is taken as 1 mole, that means 1 gram mole, we have studied that the volume is 22.4 liter. Okay. STP means standard temperature and pressure. The standard temperature is 273 Kelvin. Standard pressure is 101325 Pascal. Okay. So, for 1 mole of any gas at STP, the volume is 22.4 liter. Okay. 1 mole means 1 gram mole. 1 gram mole of any gas. 1 gram mole of hydrogen gives 22.4 liter at STP. 1 gram mole of nitrogen gives 22.4 liter. 1 gram mole of oxygen gives 22.4 liter. Okay. Then, if I take it as number of moles is 1 kilomole. Okay. Instead of 1 gram mole, 1 kilomole. Then volume equal to 22.4 meter cube, because 1 meter cube is equal to 1000 liter and 1 kilomole is equal to 1000 gram mole. Okay. So, 1 kilomole of any gas at STP gives 22.4 meter cube. Okay. 22.4 meter cube. Clear? Standard temperature and pressure. And these calculations are based on ideal gas equation, PV is equal to nRT. Then equal masses of methane and oxygen are mixed in an empty container at a 25 degree Celsius. The mole fraction of oxygen. Okay. Equal masses of methane and oxygen. Suppose we can take a methane and oxygen, x gram. Okay. X gram methane and x gram oxygen. Then the question is mole fraction of oxygen. So, first we have to calculate number of moles of methane and number of moles of oxygen. Okay. Methane number of moles, x divided by 12 plus 4, 16. Here x divided by 32. This is number of moles of methane, this is number of moles of oxygen. The question is mole fraction of oxygen. Mole fraction means individual number of moles divided by total number of moles. So, individual number of moles is x by 32, total number of moles x by 16 plus x by 32. Okay, individual divided by total. So, x is common, then 1 by 32 divided by 1 by 16 plus 1 by 32. Okay, 1 by 16 is 2 by 32. So, 2 by 32 plus 1 by 32, 3 by 32. So, answer is 1 by 3. Okay, option B. In other ways, the molecular mass of methane is 16 and molecular mass of oxygen is 32. Okay. So, equal masses of methane and oxygen, that is the given hint in the question. So, we can take it as 32 gram of methane and oxygen. Okay, 32 gram of methane and oxygen. Instead of x, we can take it as 32 gram of methane and oxygen. The question, in this question, equal masses of methane and oxygen, that is the given data, equal masses of methane and oxygen. So, instead of x, I have to take 32 for the simplicity of calculation. I mean, comparing 16 and 32, 32 is the LCM. Okay. So, instead of x, if we take 32 gram methane and 32 gram oxygen, 32 gram methane and 32 gram oxygen, the number of moles of methane is 32 by 16, 2. The number of moles of oxygen is 32 by 32, 1. Then mole fraction of oxygen, 1 divided by 1 plus 2, 1 by 3. Okay. Instead of x by 32 divided by x by 16 plus x by 32, the 32 by 32, the value is 1, 32 by 16, 2. So, 1 by 2 plus 1. Okay. In the case of mole fraction of oxygen, 1 by 3. Okay. Option B, 1 by 3. Okay. Anyway, you can start with x gram of methane and x gram of oxygen, or 32 gram methane and 32 gram oxygen. Okay. Then this is a previous GATE question. The weight fraction of methanol in an aqueous solution is 0.64. The mole fraction of methanol XM satisfies XM less than 0.5, XM equal to 0.5, XM between 0.5 and 0.64, XM is greater than or equal to 0.64. The basic equation is number of moles equal to given mass divided by molecular mass. This is a basic equation for calculating number of moles. Okay. In this way, we can convert mole fraction into weight fraction and weight fraction into mole fraction. Okay. Here, weight fraction is given as 0.64. Weight fraction of methanol in an aqueous solution, that means the second component is water. So, there are two components, one is CH3OH methanol, another one is water. Okay. The molecular mass of methanol 12, 15, 16, 32 and water 18 gram. So, here weight fraction is given as 0.64. So, convert into number of moles. Okay. Number of moles, weight divided by molecular mass. Similarly, number of moles of methanol 0.64 divided by 32. Okay. Mole fraction means individual number of moles divided by total number of moles. So, convert weight fraction into mole fraction. First, the 0.64 is taken as instead of weight. Okay. Divided by molecular mass, that is CH3OH molecular mass is 32, 0.64 by 32. That means number of moles of, okay, we think it as number of moles given mass by molecular mass, number of moles of methanol. Okay. So, number of moles of methanol is 0.64 by 32, then plus 64% is methanol, then remaining 36%. 0.64 is weight fraction of methanol. There are only two components, methanol and water. So, if the weight fraction of methanol is 0.64, the remaining weight fraction of water that is 0.36. So, 0.36 divided by water molecular mass 18. So, this is number of moles of methanol, here number of moles of methanol, here number of moles of water, individual number of moles divided by total number of moles. So, 0.64 by 32, 0.64 by 32 plus 0.36 by 18. So, simply we can write it as 64 by 32 divided by 64 by 32 plus 36 by 18. So, this is 2, this is 1. So, 2 by 4, that is 1 by 2, that means xm is equal to 0.5. Okay. So, for converting weight fraction into mole fraction, you think about this basic equation, that is number of moles is equal to given mass divided by molecular mass. Okay. So, for converting weight fraction into mole fraction or mole fraction into weight fraction, this is the basic equation, number of moles equal to given mass by molecular mass. So, one more question, methane is mixed with a stoichiometric proportion of oxygen and completely combusted. The number of additional specification required to determine the product flow rate and composition, option A 0, option B 1, option C 2, option D 3. This is also one of the previous GATE question. Here methane is mixed with oxygen. So, the reaction is methane plus oxygen and the products are carbon dioxide and water. So, these are the information we can get from this question. But the question is number of additional specification required to determine the product flow rate and composition. So, the amount of carbon dioxide and amount of water is required. For getting this amount of carbon dioxide and amount of water, at least the amount of one of the reactant is required. Okay, at least one of the amount of reactant is required, that means 1. Okay, number of additional specification required is 1. Okay. So, these are the basic concept in process calculation, mainly the solution based on molarity, molality, mole fraction. So, these we required for calculating material balance. Okay. These are the basic simple 1 mark questions we discussed in this session. Okay. Thank you.